to introduce my advisor, Dr. Pablo Mejia Ramos. He has a joint position between the GSE here in math education and in the math department. So his research focuses on argumentation and proving, particularly at the undergraduate level. And so today he's going to be presenting some work from one of the NSF grants that he is a PI for.
All right. Okay, so yeah, as Kristen was mentioning, this is some work that we've been conducting over some years. Thanks to some funding that we got from the NSF. I'll make sure to acknowledge everybody who was involved in that project at the end. Yeah, so okay, so the title, Reasoning from Examples and Diagrams when Constructing Mathematical Proofs. The idea here is that there's going to be some talk about reasoning when proving in mathematics, but there's going to be an underlying theme or story here about testing hypotheses in general from small-scale studies. So this is the plan of the talk. For those of you who are not familiar with the notion of proof in mathematics or may have forgotten, I'm going to talk a little bit about the role of proof in mathematics, give you a sense of the kinds of tasks that we're asking students to engage in. Then I'll jump to talking about the role of diagrams and examples in proof constructions, and then the particular types of reasonings that are associated with that. I will then move to 3 hypotheses from small-scale studies in the literature about the way that students use these diagrams and examples when constructing proofs. And those numbers there are just numbers of slides that I have, so give you a sense of how far we'll get to different places. The big part is obviously going to be discussing the large-scale study designed to investigate these 3 hypotheses. And then at the end, I'll talk about the findings and discuss what we have learned about each one of those hypotheses in this large-scale study. So yeah, the plan is to end somewhere close to 12:30. So we have time for questions. Okay, so let's talk a little bit about proof. To talk about proof, let me just remind you about the wide variety of activities that we engage in when we're learning mathematics. So when we're learning mathematics, we have new words that we have to learn and the meanings of those words. And I'm talking here all the way from high school to university level. So there's things like the words like polynomial and then root of a polynomial and the set of complex numbers that are words that are used in algebra, for example, in schools, and we need to kind of learn what those words mean. And the same thing happens in geometry, for instance, when we have words like parallelogram, then diagonals of a parallelogram, and segment bijection. All right, so there's these words, these terms, these concepts. Then there's also facts about these concepts, and we spend a lot of time in mathematics also learning about these facts. So, for example, about polynomials, we know that every non-constant single variable polynomial with complex coefficients has at least one complex root. So that's a fact about particular family of polynomials. And the same in an example in geometry. So we have the diagonals of a parallelogram bisect each other. And again, so we're using kind of the terms that we learned, to make statements about those concepts, and so they're kind of facts about those concepts. Obviously, that's not it. We also have learning new algorithms, which is this is very we spend a lot of time in mathematics education on teaching and learning new algorithms. So we have solving systems of linear equations. So as examples of that, bisecting a segment with a compass and straight edge is very common kind of algorithm that you learn in geometry. Maybe later in calculus you have calculating the derivative of a function. And then maybe later in linear algebra, things like calculating the inverse of an inverted dimensions. Okay. Now I'm not saying that I'm going to list all the different kinds of activities that we do when learning about mathematics. There are things like conjecturing. There's things like modeling situations using some of these concepts. using those algorithms to solve problems in other contexts. But what I am going to focus on here is that one of the other things that we do about when learning mathematics is learning why some of those statements are true about those concepts and why those algorithms work, right? So why do the diagonals of a parallelogram bisect each other, right? We discuss the reasons why that is the case. And the same thing with algorithms. Why does the algorithm to solve a system of linear equations work? Why does it always work? I learned the steps. Why does it work? Okay, and at different points in our education, in mathematics, we have different types of justifications that are given to these kinds of answers. And some of these justifications are more rigorous than others. I'm not gonna try to define here what proof is. It's a kind of a very heated philosophical topic. But I'll say that the more rigorous justifications are usually given that label of proof. These are the proofs in this particular context. And in mathematics education, we value developing students' appreciations for these types of justifications and developing their skills to comprehend and to construct their own proofs. So this is something that is highly valued, and this is represented, for instance, in the common core standards and practices and things like that. And one thing that I'll say is that this is true, that this is valued is true at the elementary, middle, and secondary levels, but it's particularly true at the undergraduate level, where I do my research. Now, the problem is that getting students to develop this appreciation and these skills that I was talking about is very difficult. So there's a lot of research in the field that show that students have great difficulty trying to construct some proofs to given statements. And so things together, the importance of that mathematicians and math educators give to this particular type of justification, difficulty that students have, create a space where there's been a lot of research on this particular area of proof. And in particular, there has been a lot of work on the ways in which students approach a proof construction task, where a student is is given one of these statements, these facts in a particular topic in mathematics, and they're asked to produce one of these justifications for why that statement is true. Okay, so that's kind of the few slides on proof. Hopefully by now everybody kind of remembers what a proof is in mathematics. Maybe I'm sure that at least in the context of geometry, it's very common that you encounter those early on in schools. I will now move into the particular topic of how, what kinds of reasonings are used when students are to construct these proofs or give these justifications. So in the research that I was talking about, there's this distinction between two different types of reasonings reasoning that you can use when attempting some of these problems. One of them is starting with formal definitions of the concepts in that statement that you're being asked to prove, and then using logical inference and calculation, all working within the formal representation system of proof to produce that justification. All right. So that's one way of reasoning. I'll give you an example in a second. A second way of going about attempting some of these problems is to start with informal representations of those terms instead of the formal definitions. So let's just say what those terms mean in terms of graphs or diagrams or some examples, and then constructing informal arguments using referencing those representations, and then trying to work out a way of getting that informal argument to, translating that informal argument into a formal proof. So those are kind of two ways in which you can approach this task. Of course, these are caricatures where I'm not saying that you can only use one type of reasoning at any, in one attempt. You can use both, but these are essentially two types of reasoning that can be used. And this has been documented in the literature, how students do this. And they have received the following names in a subset of that literature. So the reason is based on formal definitions that is very symbolic, logic, is called syntactic reasoning, and the reasoning that is more based on informal representations, specific examples, graphs, diagrams, and used to construct informal arguments is called semantic reasoning. Okay, so in the hypotheses that we're going to be discussing today are about these two types of reasoning. Okay, so let me give you an example. Let's say that you're giving a statement in mathematics like this one. Suppose that f of x is a differentiable even function, and prove that the derivative is an odd function. Okay, so that's a fact. You may not remember what a differentiable function means or an even function means, but you can recognize that this is just a sentence, a statement in mathematics that says something about an object, that derivative of that function, and it's the fact that it's odd. So, in what you're asking the student to do is to prove that that is indeed the case. Okay, that always, no matter what function you pick, as long as it's differentiable and even, the derivative is going to be odd. Okay, so let's see what those two different types of reasoning look like in this case. So so on the one hand, illustrating the syntactic reasoning, somebody may say, well, let's just go to the definition of these terms. What does an even function? What does it mean for a function to be even, and what does it mean for a function to be odd? And a student may write these equalities, which essentially are saying that an even function assigns the same value to x and minus x, regardless of what x is in the domain. And an odd function assigns to x and minus x values that are equal in magnitude but opposite in sign. Let's say that's a way of looking at it. And so this is the idea is that here we are referring to the formal definition of what these terms mean, and then somebody may say, well, since f of x is supposed to be an even function, then we just apply the definition. It means that it's of the first type, so that happens. But if f of minus x is equal to f of x, then the derivative of f of x is going to be the derivative of f of minus x. And then we can use a well-known theorem in mathematics, the chain rule, to say, okay, but in that case, we know that the derivative of f of minus x is just the derivative of f evaluated in minus x times the derivative of minus x, negative x, which is negative 1, so you get that. And at this point, the student may realize that, oh, look, what I have shown is that the derivative is actually an odd function because it's given to x and minus x, regardless of what x is, a value that is equal in magnitude but opposite sign. So they conclude that the function is odd. Okay, so that's kind of using only syntactic reasoning there to solve that task. On the other hand, we can have other representations that may be used, informal representations that may be used to represent these concepts of even and odd function, right? So if you were thinking about what even and odd functions are represented graphically, they're talking about functions that have graphs that, in the case of even, that are reflected on the y-axis, right? So because to x and minus x, no matter what x is, they're giving the same value, right? So it's kind of symmetric across that axis. And in the case of odd, what we have is a situation that is symmetric around that point, the origin. So x and minus x, no matter what they are, they're giving the same magnitude but opposite signs. So values that have the same magnitude but opposite signs. Okay, so some student may decide to start working on this problem using these representations instead of those ones, right? And so if that's the case, then they would say maybe, well, look, so if the function is even, it's of this type, and then, okay, and what is the derivative? They may interpret the derivative again informally by saying, well, the derivative is just giving me the slope of the function at different points, right? So, okay, so it's the slope of that tangent to that function. But then if I look at a function that is symmetrical with respect to the y-axis, then what I'm noticing is that no matter what x is, the slope of those tangents or at x and minus x are going to be opposite in terms of sign, but the same magnitude. So again, and that's what we're saying, that the derivative has as a property in order to conclude that it's odd. Okay, so here is, I don't know how many of you were able to follow more or less the arguments, but the important thing here is I hope that you realize that there's different types of reasoning being employed here in these two approaches based on the type of representations that they're using and the kind of arguments that they're constructing. Okay. And while the concept of even function and odd function and calculus in general may be strange to many of you, hopefully you still remember that even in school mathematics, you have you had problems where you could approach visually or entirely symbolically, right? So you had situations in which you had to solve a word problem, and one way of going about it was just, go straight to the symbolism, set up the equations, go with the algorithm, and then find your solution. Whereas another way of going about it would be, represented informally, maybe using a graph or a diagram, try to interpret, say what that diagram gives you in terms of information to solve the problem, and then reason maybe informally, then formalize that argument to get a justification for your problem. So again, even if the content of this particular example maybe strange to some of you, hopefully the idea that there's this two different ways of reasoning in mathematics is familiar in terms of your own experience working in school mathematics, for instance. Okay, so there you go. So we have, let me just go back 1 second to remind everybody. So we have these two different types of reasoning, syntactic and semantic reasoning. We're talking about the particular task of asking students to construct this rigorous argument to justify a given claim in mathematics. And then we're going to go and see what the literature says about these different types of reasoning.
Pablo, how's the one on the right of proof?
What was that?
How is the one on the right of proof?
That's a good question. Neither of these, well, I guess this one could be turned into a proof by adding some further justifications. I'm not talking, and this one would probably not be qualified as a proof by most mathematicians or math educators. The point here, and this is very important, is not about the product itself, but the way in which you solve the problem. So this is very important. So you can have two people who have exactly the same proof at the end, but the way of constructing that proof was completely different. You could imagine that this person would have, well, in this case, given that this person used the chain rule, probably not, but I could have created another argument here that was entirely, symbolic, that would potentially be the product of this same type of argument here. So yeah, it's very important here. We're talking about the way in which you approach the problem, again, types of reasonings that you use, and not necessarily what the product itself looks like, what the argument, the final argument looks like. Yes?
Can you go back a slide or two?
Yep.
Go back one and first. Oh, okay. So here, when you're talking about these types of reasoning, is this scheme is for students, novices, or is this scheme for anybody, for everybody?
Anybody really. So this language has been used to describe individuals working on proof construction tasks at different levels, from school children to all the way to research mathematicians. So this is just like a characterizations of different types of reasoning that are used across.
So do you want me to ask a question now or wait?
Well, I'm curious now.
So what I'm thinking about, I'm trying to analogize between, say, Larkin and Simon's perspective that an expert looks at an equation. They're not thinking about the syntactic level. They're immediately going to the mental model underlying it, right? So I'm wondering what's different about this domain, if in fact you're saying that even experts would approach it either at the syntactic level or the semantic level. I would think experts, by analogy, the Larkin and Simon and all kinds of other work and expertise, would go right to the semantic level.
Well, that's interesting. That may depend, and this is part of the story that I'll be ending, kind of telling today. But if you think of a problem, if you give to a mathematician a problem that is really simple, that can be easily solved by just applying an algorithm, that's probably what they'll do. Right there, they won't go to the whole model and So
it is relative to their level of expertise.
It's relative to different things, and so there are different factors that play into how you would go about what route you go and what kind of reasoning you use. But it's certainly not a case the case is not made in the literature that once you become an expert you move to certain types of reasoning. I mean, the suggestion again, I think we're gonna get a little bit more of
Okay,
this as we talk about the different factors. Okay, so there you go. 3 hypotheses. So the first hypothesis is what we call the reluctance of usage hypothesis. So what this hypothesis says, is that mathematics majors are reluctant to engage in semantic reasoning when constructing proofs. Okay, so the idea is that the second type of reasoning that I display here is actually rare when you ask math majors to construct proofs. And furthermore, several researchers have suggested that this may be part of the reason why students find it hard. They're working within a system of representations that is completely alien to them, lacking meaning. Maybe if they did more of the semantic reasoning, they would do better approaching these tasks. Now, there's two main reasons given for this reluctance in the literature. So on the one hand, we have researchers saying, well, part of the problem, or maybe the problem is that the students don't know this, are not very familiar with this representation system, right? So maybe they just don't know how to represent some of these concepts informally, using graphs and using diagrams and so on and so forth. And maybe the reason is because so much of what mathematics education looks like is at least at the undergraduate level is this reliance on the symbolism. So that's one account. The second one is, well, look, even if they are able to produce those representations and work with them, students actually don't see them as relevant for the particular task of constructing a formal proof. So these other researchers have given evidence of students who are able to make the diagrams, for example, about in the particular case of Raman, was in that specific example that I gave you about the even and odd function, where students are able to make the graphs and represent these concepts informally, but then they don't see this as being relevant to constructing the proofs that they're being asked to construct. So one is about not having access to those representations, and the other one is about not seeing them as relevant. Okay, so that's kind of the first hypothesis. Mathematics majors are reluctant to engage in this kind of second type of reasoning. The second hypothesis is what we call the bimodal distribution hypothesis. And this says that most mathematics majors show either a strong propensity or a structural reluctance to engage in semantic reasoning. Okay, so what we have seen in the literature is that when conducting small-scale studies, some researchers have noticed that a subset of their population kind of tends to do this very often, using this type of informal representation, informal reasoning, whereas another subset just almost never does, and then just kind of goes to the other type of reasoning. Some of the researchers have contended then that most students can be classified as either semantic reasoners or syntactic reasoners. So this is a very important point here. You're moving away from the particular type of reasoning that you may use to, when solving a problem, to saying now that you have a style. You're a syntactic reasoner. You're a semantic reasoner. You're implying that given a particular type of reasoner, say semantic, then that person would tend to use semantic reasoning when trying to solve this type of problems, and the same thing with syntactic reasoners, right? And so that's one step of the argument here, of the hypothesis. And then the next one is that most people actually fall into one of the two extremes, right? And again, this is all based on small-scale studies. So for example, the Alcock and Simpson and the Pinto and Toll each conducted a semester-long studies on students' reasoning in real analysis. In both cases, roughly half of the students used semantic reasoning, and then probably half of the sample used syntactic reasoning. Okay, so that's the second hypothesis. The third hypothesis is that, and this is related to something that I had been discussing in the first hypothesis, is that there's a semantic advantage. This is the semantic advantage hypothesis. And it's saying that mathematics majors perform better on proof construction tasks when they use semantic reasoning. So it's kind of going at the idea that, look, this type of informal reasoning is actually very useful. Students who tend to use this type of reasoning are actually doing better in these tasks, right? And these authors' in-depth analysis show that how the students' use of informal representations allow them to make progress in proof construction tasks. So the kind of evidence that you see in these studies is you have students who use semantic reasoning and who make progress doing so in a way that you wouldn't see, the syntactic reasoners doing. So, for example, Gibson makes this point very clear by noting that using diagrams helps students complete subtasks that they were not able to complete while working with verbal symbolic representation systems alone. Okay, and then others have blamed the students' failures to write proofs. This is something that I mentioned earlier, partially on that predominance of syntactic reasoning, the idea that they were relying on this one type of reasoning syntactic may be the problem. And then, of course, well, these findings, when taken together, suggest that mathematics majors perform better in proof construction tasks when they use diagrams and examples. So these are the three hypotheses that we wanted to test. These hypotheses were emerged from small-scale studies. I think the biggest one was the Alcock and Simpson one, which had 18 students. And so it's kind of difficult to make claims about proving behaviors of a larger population based on those studies. And so what we wanted to do was investigate, these hypotheses by just taking a larger sample of mathematics majors. So that was the idea, scaling up these previous studies to kind of investigate these three hypotheses that I just mentioned. Okay, so what were our research questions? So the first thing that we were concerned or interested in was the distribution of students' use of semantic reasoning. Do most students use semantic reasoning on only a few of the tasks that are given? So the reluctance hypothesis. And do most students use semantic reasoning on either nearly all or nearly none? So the bimodal distribution hypothesis. And then the second main question is the frequency of students' use of semantic reasoning correlated with academic achievement? So this is the semantic advantage hypothesis, right? Do the students who use this reasoning with more actually do better? So that was those were kind of the two main questions. And this is what we did. We recruited 73 mathematics majors. These mathematics majors had already completed the basic cycle, calculus cycle. They had already taken an introduction to proof course, so they knew what proofs were, and they had already taken some proof-based courses. In particular, all of them had taken a linear algebra proof-based course. So again, the important thing here is that these 73 mathematics majors had passed these courses, were somewhat successful, knew what proofs were about, and had some experience constructing. There were two individual class-based interviews, each one lasting around 90 minutes. These interviews were videotaped, and then for this presentation, I'm going to focus on the interview that had all the tasks coming from calculus. There was another one from linear algebra. And the instruction here was very simple. It's a typical think aloud protocol. We asked students to think aloud as they were working on these tasks. I'll show them to you in a second. They were given the task one at a time, at a random order. They were asked to write their final proofs as if they were handing them for the final exam of a course. So this is related to Drew's question earlier. So the idea is that all of these participants were asked explicitly to produce something that they would turn in for credit. So that essentially get to the last point of the process of producing a proof, right? And then they were given 15 minutes to work on each task. This is roughly what we give students in a proof important thing for us with these tasks was this: one, we would have a kind of a variation of levels of difficulty, and two, that each one of these tasks were accessible to students using either one of the two approaches that I discussed. So these tasks were designed with the help of mathematicians and an advisory board, and were designed to be tasks that we had a good sense that students had the tools to approach either semantically or syntactically, right? Okay, and the different level of difficulty, again, I guess going back to that, really easy tasks where the syntactic approach simply works, without much problem, and then you saw everybody using that. You couldn't really tell if that was. I mean, that's not the interesting claim that we want to make about students using one or another. So we wanted to see what happened with tasks of different difficulty, and so this one was actually the easiest task here, the one that I discussed earlier, and this one, the last one, was the most difficult one. The difficulty was based on students' responses to this in a finite manner. Okay, so another important thing here is that at any point in the interviews, participants had access to two resources. So on the one hand, they had a computer with a graphing calculator that allowed them to graph functions and kind of make basic calculations. And on the other hand, they had a definition and an example of each concept used in the study if they asked for it, so if they didn't know these concepts. This is important here because what we didn't want, we wanted students to be able to understand the statements, of course, and in the chance that they didn't understand the statements, we wanted to give them something that had representations that were both semantic and syntactic, right? So we wouldn't only give them the formal definition. So for the even function, for example, if anybody asked for the definition of even function, what they would get in the pamphlet would be, kind of the formal definition, then saying, look, an example of an even function then is f of x equals x squared, which looks like the one that I just showed you. And then, look, you can interpret even functions as being symmetrical across the y-axis, right? Again, the idea here is that the resources were there. We really wanted to see whether the way that they decided to proceed was because of a preference and not because of lack of resources. Okay, and then in terms of achievement, we collected information on participants' performance. Essentially 3 grades. One, the transition to proof course, the intro to proof, the introduction to real analysis course, and the linear algebra course. The important thing here is that the last 2 courses, so the first one is the course that is supposed to introduce students to the notion of proof in mathematics. And the last 2 courses are the first courses that are proof-based that they take after taking that introductory course, right? And so we collected those 3 grades. Okay, so the analysis was done as follows. We had 2 coders code each 6% of the data. There was a 20% overlap that was randomly chosen to test inter-grader reliability. Coders noted every time that an informal representation was used. So they flagged every time a participant used a diagram, for example, or consider a particular example. And whenever a participant used an informal representation in their approach, that approach was then termed semantic. So at least, that was the bar. At least one semantic representation was used. Furthermore, we were not only concerned about if a diagram or an example had been used, we also wanted to know how it had been used. So we kind of followed up each informal representation by looking at different types of actions that students had performed on that representation. And we computed 2 measures for proof performance. One of them, what we call the advanced mathematics course performance, was essentially their average on those 3 grades for the grades of those 2 courses, and then the number of valid proofs that they had constructed, with the exception of insignificant or minor errors. So essentially, if the proof was correct, was coded as correct. Okay, what did we find? So this is the first table of findings with respect to those last measures. We have the number of valid proofs produced from the maximum would have been 7 in this case. So the maximum in our sample was 6. The mean just tells you that this is hard. This is really hard. So the average valid proof produced was 1.77. This is consistent with the literature, and yeah, and I guess for what we cared about, it didn't matter so much whether they were able to produce the proof. It was the approaches that we were studying, right? So this is kind of important. The average grade on those 3 courses was 3.23, and those are the ranges for minimum and maximum. And then the semantic approaches, the number of tasks from 0 to 7 that they approached semantically, the mean was 4.25. There was a significant, a strong positive correlation between the 2 measures of academic advancement, so the AMCP and the valid proofs. And this indicates that the ability to prove non-routine problems in calculus in a 15-minute span is a predictor of success in advanced mathematics. Okay, so that's about the performance. What about the distributions? So here what we have is, on the x-axis, we have the number of tasks approached semantically from 0 to 7, and then the number of participants that approach that number of tasks semantically. So what would you predict the distribution to be, right? So how many students having 0 tasks approach semantically, or how many participants having exactly five problems approach semantically? Well, if you were among the researchers who believe the reluctance of usage hypotheses, you would expect some sort of distribution like this. I'm just making this up, right? Something that is heavy on that tail, essentially saying, look, most students don't use any semantic representations, and then so the number of semantic approaches is just very small. However, if you were somebody who believed the bimodal distribution hypothesis, this is something that you would expect. So what you're telling me is that most participants either do not use semantic representations or use almost entirely semantic representations, right? So the bimodal distribution hypothesis is telling us that the tails will be very heavy, there will be a thin middle, right? Okay, this is what we found. This was the actual distribution of participant semantic approaches in our study. So there are different things to note here. Obviously, everybody used a semantic representation in at least one of problem given. Second, the majority of those participants, 71%, had semantic approaches on at least 4 of the tasks. So again, this is kind of going against that reluctance of usage hypothesis. And in terms of the bimodal distribution, well, it's easy to see here that almost 2/3 of the participants are right there in the middle, right? So 46 participants, which are 2/3 of the participants, are right there in the middle. Okay, one thing that we noticed when we were doing this analysis is that out of the 633 semantic representation, 86% of those were diagrams. So remember, the representation were usually either diagrams or examples, specific examples, and 86% of them were diagrams. So we wanted to do the analysis separately, and the results are similar. So this is the distribution focusing only on diagram usage, and then you have similar results about well, most students, participants spending using diagrams in at least 4 of the tasks, and then having a 2/3 of the population in the middle. We did the same thing with the examples. We have a slightly more slanted distribution towards the left, but again, similar result. Okay. So what about the correlation of semantic reasoning and academic achievement? So that table that I showed you earlier. So what we found was that correlation was weak. So with respect to that, the semantic advantage hypothesis, the one that says that students who would use more semantic representations or reason semantically more would be more likely to have to be successful constructing proofs. That doesn't seem to be the case, or at least it didn't come across in our data. So the correlation between our measures of success, again, remember those were the grades and their number of valid proofs in their semantic approaches was very small. And when we did the analysis separately for diagrams and example usage, we had a similar situation. So weak correlations overall with success. Okay, So let me jump to the discussion about each one of those hypotheses. Okay, so hypothesis one was the reluctance of users hypothesis. We found no evidence that mathematics majors are reluctant to engage in semantic reasoning or constructing proofs. And then why is this? Well, one reason may be that a few of the studies, the two that I have here in particular, where this reluctance was observed was in domains like group theory and elementary logic. So what does that mean? That means that, well, there's a difference between those fields in the topic of calculus where students were working in these problems. It could be that they were reluctant to use semantic representations in those topics because of the topic itself. It's just a topic that doesn't lend itself to reasoning with diagrams or examples, or not as much as you would do with calculus, right? So for the calculus task, students had a conceptual resources needed to engage in this visual reasoning. So they are used to working with these representations of functions, for instance. And so we would expect that they would be familiar with those presentations by the time that they had completed those 4 courses in calculus that they take. Furthermore, the graphic application that we gave them made them have access to constructing those graphs. So it may be the case that the reluctance that we observed in previous studies was not a reluctance per se, but rather that the participants lacked the access to those informal representations, right? And so this is a problem of this may be a problem of generalizing from studies that are conducted in one setting, in one particular mathematical topic, to just mathematics in general. There may be important differences there that we need to take into account when we're making these claims. So, and to be fair, I think part of the problem is not the authors themselves. I mean, sometimes it is. Sometimes it's just the kind of route that some of these findings take through the literature, right? To the point that today people are scared about getting cancer from eating, one slice of bacon, right? So it's this notion that suddenly, you have a study that says something, and then somebody uses it in a particular different way, and then they make a bigger claim, and then those guys claim all of these, and then so on and so forth. So that may be part of the problem. So that's with respect to the first hypothesis, the reluctance of each hypothesis. What about the second one? So again, the second hypothesis, which was the bimodal distribution hypothesis, we found no evidence that this is true. We found no evidence of that mathematics majors show either a strong or a propensity to using or a strong reluctance to using semantic reasoning. Now, this particular finding wouldn't be surprising to educational psychologists who work in cognitive styles. The literature of cognitive styles is full of these grandiose claims about cognitive styles based on not enough evidence, right? And this is, the chapter by Caulfield et al. This is discussed at length. But in particular, one of these sources warns that the cognitive strategy that one invokes may be dependent upon the demands of the task as well as cultural and environmental factors. And the demands of the task is what I was saying earlier about this issue about difficulty, right? If I give you problems that are very easily solvable by easily applying one algorithm, that is syntactic, and that doesn't say much about your preference or your style of thinking more than the kind of problems that you're giving. So the warning here is kind of general to cognitive style research, but in particular to how it applies to this particular topic of proving styles in mathematics. So the recommendations, of course, are that one should infer students have a cognitive style based on completion of a large number of examples of tasks instead of small. And the same thing could happen with the topic itself, right? So it may be that students are more likely to use a particular type of reasoning in one area, but not others. So we have to be worried not only about the number of problems that we give. It's diversity of tasks in general, not only number of tasks, but diversity in terms of topic and area. And the problem here is that these judgments are usually done in the literature based on a very small number tasks. Sometimes a single task, which is problematic. Some of these factors have been discussed in a paper that we're getting out soon, that is coming out soon. Some of those factors include things like, the way that the participant has seen this material presented, the amount of time that he or she is given to solve the task, their familiarity with the representation, so on and so forth. Okay, and then finally, with respect to our last hypothesis, the semantic advantage hypothesis, we found again no evidence that mathematics majors perform better in construction tasks, proof of construction tasks using semantic reasoning. And these challenges in general, a large subset of the literature that focuses on example usage and diagram usage. What is important here is that this obviously does not contradict the fact that these representations can potentially be useful, right, to solve these problems. And again, there's this kind of mismatch between the actual findings of the small-scale studies to how they're, how that develops into how they're cited. So if I have a student that, if I document a few students who have actually used semantic or informal representations quite successfully when solving this particular type of task, what I have found is that this type, and I can tie it, in my study to their success, to the use of representation. What I can conclude is that, this can be useful, right? But there's a step there to saying then that just tends to be useful, or that if students are given these representations, that they will be successful using them, right? And I think that's part of the problem, where some of the literature that responds to this kind of critique is actually saying, no, but look, I have students who are actually quite successful. And you're like, yeah, but there's a disconnect there in the argument. In particular, mathematics majors may lack the resources needed in making varied inferences for diagrams and examples and translating visual arguments into formal proof. This is something that we have been working with Keith in our group here. Using informal representations like diagrams and examples is not simple for students. It's a hard task. It's obviously quite encouraging when you see a student who is able to use them, have them use the power that those representations are giving them. But that's not usually the case. It's hard to initially reason with this kind of mathematical object. And indeed, there are some suggestions in the literature that using this type of representations can cause some difficulties to students in this particular type of task. It is also possible, and this is something that we that we discussed in that manuscript that I was describing earlier, that time is an issue. So it could be that engaging in semantic reasoning is something that students know requires a lot of time. So if I'm only given 15 minutes to solve a problem, I may just not go that route. I may just try to push the symbols and hope for the best, right? So time could be, again, resources here, but in this particular case, time can be an issue. And the problem here again is that this 15 is not artificial at all. This is usually what the time we give students to construct some of the proofs that I showed in exam settings. So if we want math majors to reap the benefits of using this kind of reasoning, then we would have to provide assessments that afford them to do so. So that ends the discussion about those three hypotheses. As I said in the beginning, this research was done with a group of people: Jimmy De La Torre, Evan Fuller, and Keith. And Keith were co-PIs in that grant. Kevin, Kristen, Aaron, and Bo were all research assistants. They helped us collect code. This was a lot of interview data from many students, so they received a lot of credit here. And obviously, the NSF for providing the funds to conduct this research. That's it.
We have 10 minutes. So I was bothered by the fact that whereas about 4.5 problems, on average, students use semantic reasoning for 4.5 of the 7 problems, but only got 1.5 problems correct, more or less. So that means only 1/3 of the time were they able to take the semantic reasoning that they started and end up with something which approximated truth. And so, so that's a little bit bothersome. It suggests to me that maybe you classified a student as having done semantic reasoning if they just put something down and weren't able to follow it through. So I know, for example, on my exams, I find students write all sorts of things, draw all sorts of pictures, without having any real understanding of what they're drawing. And so I classify that not as semantic, I wouldn't classify that as semantic reasoning, but I would classify that as doodling. And so the question is, was your coding, when you coded a student's behavior on a certain problem, were you perhaps too easily led to classify it as semantic reasoning, or even syntactic reasoning, or any reasoning whatsoever?
So yeah, that's a really good question. So 2 things here. The first one is the fact that they did so poorly. Again, I think we're starting to understand that using this type of representations and this type of reasoning is harder than we thought. So I guess we're starting to be less surprised by that particular finding, even though it is, given the history in math education of encouraging students to work with informal representations, that's not what we expected. But with the coding itself, I completely agree. That's something that we definitely took into account, and we actually spent a couple of papers going back and forth with some colleagues in England where we're discussing this kind of coding issue of to what extent doing this kind of thing where you just use the use of one representation as being representative of the whole approach. What we also did, so thinking that would be not enough, what we also did was that we got into this very complicated coding scheme where, as I said before, one of the things that we did was follow the types of actions that students performed on that particular representation, right? And so we actually coded for all different types of actions that they did. Did they only use the representation to verify a particular statement? Or did they use it to make an inference about what they were talking about? Did they use it simply to represent it? Oh, there's an even function, forget about it, move on, right? And then we gave weight to those different kinds of actions, right? So that somebody who actually used the representation to construct an informal argument was given a greater weight than somebody who only used it for a particular one. That gives you exactly the same result. Exactly the same result as this does. So when we're now reporting this, we're now going back to the simplest coding scheme that says, well, look, actually it's equivalent to the other one. So doing what you're suggesting, which we also thought could make a difference, doesn't.
Well, I think in reporting the results, if you just
you have to make that clear.
You're going to let yourself in for a lot of objections if you don't make it clear that
that's a good one.
You just said.
That's a good one.
So I wondered if you, getting back to my earlier point, like earlier kind of ballpark topic, if you use regression and modeled item difficulty in the model, whether you might get a little more a better empirical handle on these data, because it's really about item difficulty, right? Although, as this man just pointed out, a lot of, they didn't get a lot of the items correct, right?
Right.
So that's where I would worry you wouldn't get an effect because they didn't get it correct. But I don't know, I think regression could be a useful thing, modeling item difficulty.
We did that, it
Didn't pan out because of this issue of difficulty?
yeah, I mean,
It could be right. There's not enough space.
No.
I have a question about using examples to prove something, because if we use this example, it does not mean we can exhaust all examples.
Right.
For example, if we want to prove like all fruits are round, I can show you an apple and then it supports our conclusion. But if how about if I show a banana?
Right.
So like I think there is some cultural difference, like this kind of the semantic proof. If I use an example or a specific diagram to do the proof in China high school, I don't think our student will get any points for this.
Yeah, I'm sorry. Maybe I wasn't as clear as I should have been. You're absolutely right. So the problem here is when these statements are made are general statements. You know, every polynomial has this property. Every parallelogram has this property. One example of semantic reasoning is going and checking that statement with one example, right? That doesn't get you very far, right? That's not a proof. It's just checking that one particular example within that large set, which often has an infinite number of elements, satisfies the theorem. That is one example of usage, but that is not the only one.
Mm-hmm.
So if you think about this particular example that I gave here.
Yeah, this is like square.
Right, but the idea is that there are examples that can be used generically. So
you have to use an example that can be generic.
Right, so the idea is some examples, there are ways of using examples generically so that you are not focusing on the specific information of the example, but kind of on the features that any example would have.
Okay.
So even if this is a kind of a quadratic, this is f of x equals x squared, the argument that I gave here about the tangents to the graph work regardless of what the function does, as long as it has the property that it's an even function.
I think that's a very difficult part.
Right, and again, I think this is tied to what Joe was saying. Again, there are different things that you can do with examples when you're approaching a proof construction task. Some of them are very simple, as you say, just verifying that the theorem is true with one example, kind of just gotta get a sense of what the statement is saying. But there are more sophisticated way of using it, and some of those are using what we call generic examples, where you get at the reasons of why this thing works by looking at how it works in a generic example. Now, one thing that we've done with the data that we have is that we looked at the students, and I think this is also addressing Joe's point. We look at the students that were actually successful in translating, when they had an informal argument, we were actually successful at translating those into formal proofs to see if we could get some features of what those arguments had or what needed to be done in order to do that difficult step of once you have an informal argument to turn it into a proof. And so we kind of have done that as well too. Yeah.
Yeah, so you had one comment in there about the interaction of tasks and reasoning. If you looked at it from not the individual perspective, but from the task perspective, would you get differences in reasoning adopted by items? And the other piece is when you drew this sample, did they have exposure to different kinds of teaching that might have explained some of the variation as well?
So one thing we did was I forget about that. We took into account the teachers who had taught them the course.
The problem was there weren't enough people who had any one teacher to make any sense. So we had somebody who had 4 people in this class, 5 people in that class.
Right. So yeah, we tried to take that into account, but
if we just didn't have the sample size.
But yeah, so what we did was we tracked who had taught each one of those courses per participant. But it wasn't, that's right, it wasn't big enough.
I should say we also did look at the items by difficulty. The difficult items did tend to attract more semantic reasoning. The most obvious hypothesis being when you're not sure what to do, you try more things. However, even if we took into account the level of difficulty of the problem and then the success rate and aggregated it across that, we still didn't see the people who did semantic reasoning in that case actually did slightly worse. The correlation was insignificant but negative when we factor that out.
Yeah, but I'm not talking just difficulty. I mean, there may be other attributes of the items that lend themselves to or encourage certain kinds of reasoning or not. So if you took the 7 items and said what's the frequency of strategic strategy.
But then you would have to, right. And they just theoretically kind of think, what were the features of each difference.
But one of the things is, even if you take the broad, so across the 7 items, you're getting a broad picture of how often they do these things. It's not only is it not creating success in these tasks, but it's also not correlating with grades.
Right, no, I get that. Right, and that's why I wonder if it's just. is
No,
this
but I see
really an
what
item?
you're saying in terms of, I mean,
It would be easy to do.
right. Yeah, one thing that you, I don't know if this is what you're getting at, is that obviously these are not random items, right? In a sense, they have certain properties, and we kind of try to, as we were creating the items, to have, as I said, kind of a wide variety of items with regards to, what kinds of informal representations they would be using. So for this one, it's just trying specific numbers, or whether they were using graphs or not, and then also level of difficulty and whatnot. But obviously, there may be other things.
Basically, I mean, the question is, so you have a lot of variation among individuals when you look at it the way you've been looking at it. But if you looked at it at an item perspective, I mean, one potential outcome is that in fact you have very little variation among individuals, or much less in variation, that it's really a function of item.
Right.
That's, you get that same variation.
Right.
When you look at it.
Yeah, sorry, Victoria?
Going back to what the two people in the front were saying, and I'm not sure if you answered it already, but did you notice if the students who were successful in translating were successful because they were able to produce these generic examples that you were talking about versus very narrow examples that are not always true? Remember when we were talking about the
Right. So we identified to what extent to what level of detail do I give an answer?
You can tell me later.
Yeah. Is one of the three things that we found that students did was related to being able to what we call translate a given warrant. So a step that was key in the argument that rely entirely on the semantic representations and being able to translate that into something that is acceptable in a proof. So yeah, the short answer is yes. One of the things that they did was related to that.
I have another question. I don't know if there's time.
How quick is it?
Okay, I'll ask them after.
Okay.
My meeting.
Thank you very, very much for coming today and sharing your work. Next week, Dr. Roski will be here.
I'll just give you our